Hi, I'm Ben-Yaakov. This presentation is entitled Answer to Riddle, Hidden Feedback Loop Resolved. So this is an answer to a riddle that I've posted earlier. And let me go over this riddle very quickly. Here I'm showing a synchronous buck converter, two transistor, inductor, filter capacitor, and this resistor represents the load. Now we know that at steady state, and this is without outside feedback, the average voltage at this point is due to this pulsating voltage. There's a duty cycle here, and the average is V in over the duty cycle. And then we know that the average voltage across the inductor, or volt second, summing it up, is zero. So therefore, this voltage here is equal to the output voltage, from which we get that the voltage transfer ratio is the duty cycle. So this is trivial. But the question is the following. This is correct, assuming that at steady state, the volt second is zero, that is, the average voltage is zero. And the question is now, why is it stable? Why is the output not, say, going up to higher value or going down to zero? Why is it that this output voltage is stable in open loop? Again, if we assume that the volt second across the inductor is zero and the average voltage is zero, then obviously we have this output voltage. But why is this assumption? So here is the riddle. What is the hidden feedback loop that keeps the output voltage stable? Find the open loop and closed loop gains of this feedback loop. Now, for simplifying matters, we are assuming that there is no capacitor and that the inductor is large and the frequency is high. So this sort of simplified the system so it's not a second order. And in fact, it's a very simple solution. You can sort of write it on the back of the envelope or actually by inspection. So here is my solution. If we look at an inductor, here is the state equation of the inductor. The voltage difference between the midpoint and the output is equal to L di dt. Now for a small signal and sinusoidal waveform, we can say that this derivative is S over I. S is the Laplace variable. So the current now is therefore the difference between these voltages times 1 over SL. Now I can represent this equation this way. We have this summing point, which is the difference between these two voltages, and then this is multiplied by this block, which is 1 over SL. Okay, so this is one way sort of to represent what is happening with an inductor. Now in our case, the current is passing through the resistor, so the output voltage is I times R. So this I, this current, is now multiplied by a resistor. So I can add here another block, and I times R now is V out, and this is the V out that goes into here on this side, which is the difference between the two, okay? So clearly we have here a negative feedback loop. So in this feedback loop, the gain, the open loop gain, there's no beta here, it's going directly back here. The open loop gain is 1 over SL over R, okay, R over SL. And the closed loop from here to here is, of course, this value here, R over SL, 1 plus R over SL. Or writing it this way, well, this is well known, of course. This is like a low-pass filter. There's nothing new about it, but we represent it in a feedback loop, so we understand that this point is going to be stable, but of course we have a first-order response. Now for DC, S is 0, so we have a gain of 1, which is the situation at steady state in this buck converter. So this is the end of this very short answer. I thank you very much for your attention.